All right, so let's go ahead and work on our linear elastic cubic material problem. So we have a block of aluminum. So aluminum, we know that has a Young's modulus of 100 gigapascal. When we're doing problem solving for basically any mechanics problem, first thing we want to do is set up our coordinate system, similar to our statics and dynamics. 2, we need to determine our material property. And then 3, write out our fundamental equations. So metal, 100 gigapascal, approximately you could estimate Poisson ratio is 0.3. And we're told that there's an applied force of 18 kilonewtons here. And we're asked to calculate the stress, the strain, final length in 3 direction, final length in 1 direction, final length in the 2 direction. And then flip it as if we were going to be basically analyzing this problem in compression. So our force is 18 kilonewton. So, if that's correct, yes. And it's positive. So we have our coordinate system here. We have our material properties. And actually, let's go ahead and plug those into Mathematica right now. So y equals 100 times 10 to the 9. Our nu is equal to 0.3. And voila. It's going. Or also, let's just say that our force is equal to 18 times 10 to the 3 kilo, so 10 to the 3 newtons. So what is our cross-sectional area here? Well, it's going to be this distance times this distance here. So 0.1 times 0.08. So our area equals 0.08 times 0.1. So our stress, or our sig, because normal stress, force over A naught, it's going to be 2.25 times 10 to the 6 Newton. If we're calculating the strain in this direction, we're looking at the change in this dimension. But we know that stress is equal to, if we're in the linear elastic regime, this expression. So we can solve for that strain as so. So we can say solve sig equals y times epsilon. And this would be our strain value here. So, fantastic. But we're asked, what is the final length in these other directions? Now, this is the strain in basically this 3 direction, or the 3 direction, but we'll kind of leave that for now. What's happening in the other direction? Well, they're shrinking, right? So we've actually already defined our Poisson ratio. So our Poisson ratio was defined here. Our basically the lateral strain over the axial strain. So our Poisson ratio nu, so our nu is going to be equal to minus this strain in the 3 direction over basically the strain in the 1 or the strain, actually lateral strain, excuse me. So this will be basically the 1 or the 2 direction over the strain in the 3 direction. So we can also solve for that, and they'll be equal because in this instance, the strains, actually they must be equal because they're both lateral. So nu is equal to minus E1 divided by E, we'll call this E3, or epsilon 3. And those would be the values. And you see it's negative, right? And that should make sense because, again, it should contract. You can also rewrite this as well. So we can say that actually nu is equal to minus E1 over, we can move this over here, stress over here, and we should get the same value. So we can say solve nu is equal minus E1 divided by sig divided by y. And we get the same value. Fantastic. So what about the final dimensions? Well, the final dimension 3 will be equal to L3 final minus L3 initial, which is 0.03, divided by 0.03. So our final length in the 3 direction would be this. And we can use the same expression to find the final length in the 1 direction would be L1 minus 0.1 divided by 0.1. And we can do the same thing here. Again, it's contracting, which makes sense. And we can do the same thing for final length in the 2 direction. And the 2 direction will be the 0.08, 0.08, 0.08, and voila. What would happen if we were to solve this for compression? The only thing that would happen would be this force would be negative. The stress would be negative. Therefore, this epsilon here would be negative. And now, when we solved for basically the strain in these other directions, here and here, this strain now becomes positive because it's popping out, right? And that should make sense here. So we can actually plug this in. Actually, we'll plug this in here. So our final dimension here should be less than 0.03, which it is. Great. And then this should be positive here. We'll put it here. We'll put it here. These should grow. Greater than 0.08. Greater than 0.1. Fantastic. I love solid mechanics. So next time, we're going to get into bending. And we'll see you in the next video. Thanks. Bye.